Afternoon, everybody. My name is Alexandra, joining you today from the Washington, D.C. office. Welcome to Interface Engineering's 2025 Educational Webinar Series event. Today's topic, Are You Microgrid Ready? Thanks for logging in with us. I'm just going to do a quick overview of the company. Interface is a 100% employee-owned, multidisciplinary engineering firm, known particularly for sustainable design and innovative solutions, both for new and existing buildings. From our start back in 1969, we had just 4 employees, and now we are a nationally recognized consultancy with over 260 LEED certified projects and multiple zero energy buildings in our portfolio. We have 12 offices across the country with our locations listed below, offering a wide range of services and expertise with what is now quite a large team of over 200 professionals compared to our beginnings of just 4. And a little bit of an overview of what we're going to be using. We have the GoToWebinar meeting platform. You may have the web version, or you may have another if you are on a different device. However, in both, you have the option to put questions in the question field. And this is something that I want to encourage you to do throughout the presentation. Just as you think of something, go ahead and put your question in. It won't interrupt anything. We'll just get to all of them at the end. Until then, all audience microphones will be muted, so we don't have to worry about that either. And at the very end, the recording that is made will be available on a YouTube channel, and we'll send out that link to everybody. Interface is an approved AIA CES provider, and for today's course, you'll earn 1 learning unit. All attendees will either receive a course completion certificate, or if you have put in your AIA number when you registered, we'll directly report that attendance for you. Again, at the end, we will leave a little bit of time for the questions, and if we do not get to all of them, along with the certificates and recordings, we'll send out an elaboration of the posted questions with answers. So, to our presentation itself, we are going to be led by 2 of our principals, Craig Burton and Cody Bargoltz. Craig focuses on analysis and integration of high-performance design strategies for both new and existing buildings and urban environments. Concentrating on the intersection of architecture and engineering practices, he leverages performance data, analytics, and whole life cycle costing to advocate for higher performance solutions. His expertise spans from conducting energy audits on existing buildings to designing an energy positive master plan for an international expo in Kazakhstan. So quite a span there. And Cody is a LEED accredited professional with certified lighting consultant, bringing a strong background in design, project management, construction supervision, and cost estimation. He specializes in electrical systems for schools, historic buildings, libraries, recreational centers, healthcare facilities, much more, designing medium and low voltage power distribution, lighting and controls, grounding, structured cabling, fire alarm, and security systems. Again, really, really a wide range, so you guys have a lot of expertise. So please ask questions because they have a lot of knowledge for you. And with that, I'm going to give it to them so they can get right into it.
Cool. Thank you, Alexander, and thank you everyone for joining us for this webinar series. Okay, this is the course description. I'm not going to read it, but feel free to read it at your leisure. We're going to cover microgrids and really microgrid ready designs, and try to focus on the elements of a microgrid, how they manifest themselves in a project, what their roles are in making that microgrid functional. And then we'll look at some case studies, examples of how design can be applied to microgrid, and where some of the design decisions come about and how they relate to the functionality, the cost, and the implementation of a microgrid. Learning objectives for everyone on the call. We're going to understand grid and vulnerabilities and microgrid benefits. We're going to explore microgrid ready design strategies. We're going to recognize load priority principles, and we're going to incorporate renewable energy and storage opportunities into our knowledge of microgrids. Okay, with that being said, we're going to follow sort of 4 sections in this presentation. We're going to start with discussing the utility grid, the reality of the grid that we have today. We're then going to cover how a microgrid architecture looks to replicate and or solve some of the problems with existing grids, but at a much smaller scale. Then we'll then look at implementation strategies and how those come together in a project, and with a few case studies, examples of designs that we've done and projects that are in construction or built. Okay, starting with the grid, infrastructure under pressure. So the way that a utility grid operates currently is electricity is generated at power plants or distributed generation points across the nation, or actually across two nations, Canada and US together. And power is moved through to consumers through transmission and distribution systems. So using the grid, moving power from point of generation to consumers. Grid operators are responsible for looking at those three functions together. What are the available power plants? What is the way to transmit that power from the plant to the load? And what are those loads that are coming online? And then those grid operators can send price signals out to different elements of the grid to help balance in real time the supply of electricity with the demand for electricity. And that is a full-time job. It involves a lot of looking ahead forecasting, as well as analysis of what's happening in real time. But the key is that it's a balance between the supply and the demand of power. So if we accept that that is how the utility grids work in North America, a microgrid looks to bring all of that type of functionality and control and management into a smaller, discrete boundary that we might see in an actual building or a building campus project.
Okay, so what are the electricity supply and demand challenges? To start with demand growth, electricity demand is growing due to economic growth, building electrification, and new major load types coming online. The one load type that you see in the news constantly right now are data centers, and those are having a huge impact on electricity demand. But the kind of less appreciated new load is EV charging infrastructure, which we're seeing have a major impact on electricity demand everywhere we put them in. So as an example, in Oregon and Washington, with the new energy code and requirements for bringing EV charging to buildings, we have to plan for 30% of parking spaces for most building types, and in general, that accounts for more than half of the demand load for the building. And on projects, we're often needing to bring separate electrical services in just to serve the EV chargers for the site. So this is having a huge impact on the grid. And then we have capacity reduction. So retiring coal and nuclear plants across the nation are reducing available generating capacity, and this is resulting in the shortage risks. So some regions face a risk of electricity shortages, especially during peak summer and winter periods. This is primarily addressed through pricing on the grid, where when we're kind of using maximum demand, the utility starts paying more and more for the generators to come online to meet that demand. And then we have grid constraints, and that's just the ability of the transmission system and distribution system to move the power where it's needed. That is, it has a finite capacity, and this is something else you see often in the media, which they highlight these grid constraints because it does cost billions of dollars and requires major public investment and years to construct the lines needed to help bring these sources of electricity to the loads.
Cool. And then adding a little current context for some of the pricing that is coming into the electrical market now as a result of all of those factors that Cody just reviewed, is the capacity charges. So this chart looks at historical cost of a grid operator's ability to secure a megawatt of power on their system. These prices are set on an annual basis. They're auctioned off in advance of when that capacity needs to be supplied onto the grid. And what's happened, these three different regions are all East Coast regional transmission operators, RTOs. The price of capacity has increased almost 10 times over the last year, and will increase even more so next year. So this is largely due to existing capacity of power generation being sucked up by increased electrical demand, which is largely driven by data center and EV electrification. So I guess I'd caveat that with, it doesn't result in your electricity bill getting 10 times higher, but the component of your electricity bill associated with capacity charges is growing, which on an annual basis is anticipated to result in 5 to 10% increase in electrical utility bills per year, just to get that capacity reserved. So it makes the argument and the attention to microgrids and creating and producing and using power more locally to your demand ever more important. Okay, some common failure points of the existing grid that we try to solve, or that we have the opportunity to address through microgrids, are associated with weather events such as ice storms in regions of the country that the infrastructure was built not anticipating that we'd have those type of weather conditions, such as in Texas, which has had a lot of trouble with electrical infrastructure the last few years. And we anticipate, with the effects of climate change, having continued issues with, infrastructure that was not built for, a changing climate. Likewise, flooding, wildfires, the West Coast have had significant issues with wildfires and taking down electrical infrastructure that is largely transmission lines and distribution that is connecting faraway power plant generation with demands. So minimizing the amount of transmission infrastructure that is exposed to those wildfires, collecting resources closer to the actual demand and use through a microgrid helps to avoid some of these large-scale power outages. And then frequency instability is an issue that has to do with the stable operation of the utility grid, and has become more important as we've added more distributed renewable generation onto the utility grid, specifically large-scale wind, large-scale solar. These type of power generation resources don't necessarily operate 100% in sync with traditional power spinning reserve type resources. And as such, there are some challenges with maintaining the operating frequency of the AC grid. But battery energy storage systems and microgrids have a role in helping to reduce that instability. And then overloading is again an issue with existing transmission not having sufficient capacity. So we've established a little bit of a problem. We've identified that there's aspects of utility generation, transmission, distribution infrastructure that exists in the United States that we can solve. What are the opportunities for architects, for owners, for projects that we're involved with, where a microgrid might be tabled as that's a solution we might look at. So design buildings that maintain functionality during outages. So this is a real opportunity with microgrids where we can support some aspect of the building operation while the utility grid is down. Meeting client expectations for operational continuity. So continuing support beyond emergency life safety systems. So maintaining Wi-Fi, cellular networks in building. Low voltage systems that support powering cell phones, things that make a building operational to the user while working in sort of a diminished set of parameters. And then creating value through resilience features. So if a building has solar and batteries, perhaps because of it being a net zero energy project, or having a code requirement for solar on the project. Microgrids help to allow those technologies to be more applicable in other modes of operation, such as when the grid goes down, or when there's an opportunity financially to either avoid peak demand charges or participate in energy arbitrage. So positioning buildings to participate in economic opportunities around energy infrastructure.
Okay, so the microgrid solution. To start off on the microgrid solution to these grid issues, I just wanted to bring the latest definition. This has been kind of changing, so this is how it's defined now in the 2023 electrical code. An electrical power system is capable of operating in island mode, which is disconnected from the grid, and capable of being interconnected to an electrical power production and distribution network. That's what they're calling the grid, or other primary source, while operating in interactive mode. Now that interactive mode is often called grid interactive mode or blue sky mode, which includes the ability to disconnect from and reconnect to a primary source and operate in island mode. So the next slide sort of shows what that looks like in a big diagram. So the real key part of this is that first switch you see from the transformer to the building. You'll see, or to the microgrid, you'll see this grid connected mode switch and islanded mode switch. That's a key part of the definition because it's required for safety. As soon as the utility loses power, the system needs to switch instantly to island mode and disconnect from the grid so that we don't end up back feeding power back onto the grid, which is a safety issue for the utility itself. So the linemen that are going out to repair whatever went on, make changes to the switching and protection of the system, they need to be able to do that without being electrocuted. So that mode, that switch off mode is really key for a microgrid. And that's what puts you into the island mode. So your system is gonna operate like its own little island. The way that your microgrid controller works in this application is now it takes the place of the grid operator, and it starts to orchestrate which sources turn on if required, and which sources and which loads will get shed depending on your source availability. One of the key features there is the generators. You want your generators to provide redundancy and efficiency. So at least 2 generators are recommended, especially in combination with a large PV system or wind power generation system. And then the other feature there where you see the battery there, that's the energy storage system. And the battery energy storage system, that exists to reduce wear and tear on your generator and improve power quality and increase reliability for the microgrid. It also can be very profitable in regions that are allowing energy arbitrage, or where the energy arbitrage makes sense from a profitability perspective, because every time you discharge your batteries, it's basically costing you something. So when the differential is high enough, those can really help pay the battery systems off. And then in order to make this whole grid work, smart power system components are required, such as controllable circuit breakers and advanced protection and control devices. And we're going to go through in the next slides kind of each of these components so that you can see how it all fits together. So the first component, and this is a question I get a lot, is like, what do these things look like? So this is an example of what a microgrid controller looks like. The microgrid controller is simply a PLC, so a programmable logic controller. This hardware is the exact same hardware that are used in every building practically. Every commercial or larger building, which is the hardware that runs your building automation system. And these PLCs are also used basically to run every industrial process in America. So it's actually not new technology, it's tried and true and ultra reliable technology that would be operating your microgrid. One key feature on them is that the cost can vary dramatically. So a simple microgrid, the cost can be as low as $6,000 to control the microgrid, and the most expensive I've seen is the hardware cost going all the way up to $75,000 to control it. So it's really important to clearly define what your requirements are so that you get a microgrid controller that's suitable, minimally suitable to the application. Okay, so for generators are the true backbone of most microgrids, almost definitely all large microgrids. And the reason for this is that generator runtime is measured in days, not hours, or at least a lot of hours. Typically 24 hours is kind of your standard, but we can go quite a bit further than that for runtime. Of course, generators have been used for years just by themselves to power entire buildings or sites on power loss, but without a microgrid even required. But the main purpose of the microgrid is to harness the power of renewables on site and get the most out of those renewables and rely as little as possible on the generators, which is going to reduce wear and tear on your generators and lower your fuel costs. Natural gas versus diesel. So these are your main two fuel sources to select from. A key feature now of diesel to keep in mind is that advances in fuel technology, such as the introduction of hydrotreated vegetable oil, HVO fuel, make diesel an even more sustainable choice than natural gas. So you're not burning any fossil fuels with the diesel engine if you use this fuel system. And the key aspect is they're all generators designed to be compatible with it, are backwards compatible to diesel. So in an emergency, you might not be able to get this HVO fuel. So you can bring in diesel fuel trucks and it will run on those just as well. And then of course, natural gas has its benefits. Primarily, you get unlimited runtime. The generators tend to be lower maintenance, but natural gas is kind of, contrary to popular belief, extremely reliable, even in disasters. But the major downside for natural gas is as the generators get larger. Typically, once you kind of exceed 300 megawatt, but once you hit 750 and 1 meg, they become significantly more expensive. So diesel starts to show up in the larger system sizes. But the kind of idea with the microgrid where we can put in 5 or 6 generators, you probably won't need those extremely large size generators. Another consideration to keep in mind is noise consideration for generators. So critical grade sound attenuating enclosures can be almost unbelievably quiet, basically whisper quiet from just a few feet away. So the noise pollution problem is always solvable, but it's basically something that needs to be considered on every project, where you calculate back from what your sound requirement is at the property line or at kind of the nearest sensitive structure, and then you figure out what sound attenuating closure level you need is for that specific application. And then multiple generators, you'll hear me say a few times that we want at least 2. More than 2 is even better, but the more generators you have, the more you can take advantage of the microgrid's ability to bring the generators online only as required. Okay, so for the next source, PV, the goal of the PV system, besides meeting whatever regulatory requirements you have in your region or environmental goals, in the microgrid scenario, you want to generate enough power with your PV to charge batteries and to allow you to turn off the generators during the day, even when you're in islanding mode. So this system has to be oversized to about 1.4 times the average daytime load, ideally, to accomplish this, and that's going to allow you to extend the runtime past just peak generation power at noon and summer to get more use of the system during shoulder seasons, as well as in the morning and in the afternoon. So traditionally, when you're running on a generator, you need to turn off all PV generation. Otherwise, the PV system can backfeed into your generator alternator and damage it. So with a traditional system, the rule of thumb is you have to disconnect PV unless it's under 10% of the size of the generator. But with a microgrid controller, you don't need to do that because it's monitoring power flow and can prevent damage to your microgrid components. Okay, so the battery energy storage system, I get also a lot of questions. What does this look like? And they're almost all just shipping containers. Basically, they're systems completely contained within a shipping container that has all of its MEP systems built into the shipping container. And what it is, the battery energy storage system is the glue that holds your microgrid together. If clouds pass over or a rainstorm comes through, rather than shedding loads because your PV system generation capacity drops, or rather than starting up your generators, the battery energy storage system can step in and inject power when needed, and then charge back up when not needed. So without the BES, your microgrid needs generators running at all times, and those generators, they have to be sized larger to pick up the load variations. Where are they located? So these things are located outdoors. You really want to locate your battery energy storage system in almost all cases outdoors due to the fire risks associated with them. And just kind of a general rule, you want it to be sized to 80% of your peak demand load. And unfortunately, the realistic capacity is just a few hours. So typically, you'll have like 2 hours standard for a battery energy storage system, which is why those generators form the backbone to be able to give you extended runtime. But these are there when you need power quick. Okay, so the race towards the future with battery energy storage systems. So in the beginning, Microgrid scale flow batteries were the standard, as well as lithium ion batteries that were adapted from EVs into the battery energy storage systems. So the weakness of these flow batteries was mainly power density. They had an amazing strength, which is lifetime charge and discharge counts, but we had issues with power density. And innovation in the EV market and the EV market expansion has basically, through economies of scale, let lithium ion mostly displace those flow batteries. And that takes us to today, which is the latest lithium technology, lithium ion phosphate. These batteries really taken hold of the current market, and it's what we typically see now fit on projects because of their improved lifespan over lithium ion and lower reliance on rare earth metals, which reduces the cost. This is the same technology, so to put it in a maybe more common context, the lithium ion phosphate is what Tesla's using in their standard models, standard range models. And then because BES, they don't need a super high current discharge properties that nickel manganese cobalt NMC batteries need, which is what Tesla uses in their high-end cars. Lithium ion is basically perfect for buildings because we can benefit from the higher discharge counts per the rated life of the battery, and we don't actually need the extreme acceleration like the sport models have. We just need them to operate for the building. So then that leads what's coming next. So there's a lot of exciting stuff coming next for battery energy storage system, sodium ion, and there's a variety of solid state hybrid chemistries that appear to be poised to take battery energy technology to the next level. These new systems offer improved power density, lifespan, safety characteristics, and they use even more abundant materials. So we're expecting to see great things out of these. They haven't hit the mainstream market yet, but they're at the early stages of commercialization. So this is actually one of the reasons for your projects to consider avoiding large investment in battery energy storage today and planning for the future technologies that we expect to see shortly. Okay, that brings us to the smart power system. So this is what microgrid switchboard looks like. So the microgrid switchboard looks practically exactly like a normal switchboard. It has all the same features, but it adds electrically operated breakers, more advanced precise metering on each breaker, and communication infrastructure to connect it all together to your microgrid controller. The power metering and control features required to run a microgrid are simply commonly available industrial grade components that have been around for decades. So on the next slide here, we can kind of see that same switchboard described. So this particular manufacturer has the microgrid controller integrated into the switchboard on the right side there, but that's not required. In fact, most of the time it's going to be on a control panel on the wall in the electrical room, and it's just going to have communication conduits connecting over to this smart switchboard, and it can operate all of these breakers, take in all the metering remotely. These big power defense breakers, they're called, these are expensive breakers. They're significantly more expensive than the regular breaker, but each of those is actually taking the place of an automatic transfer switch. So the extra tens of thousands of dollars for these advanced breakers gets offset on your project by removing the tens of thousands of dollars in space and cost of automatic transfer switches. So in the end, you actually take up less space with a microgrid electrical distribution system. So this is just a summary of these core components. We have, to bring it all together, we have this generation sources, multiple traditional generators integrated with solar PV system, excuse me, for your generation sources. Then you have your storage system, which isn't generating power, but it's there when implemented to reduce wear and tear on your generator and fuel consumption costs. It improves power quality on your system and increases reliability. And it can also be a very profitable addition for regions that allow energy arbitrage. Then we have our smart power system components. These are your controllable circuit breakers, advanced protection and control devices, and then finally we have our control system, which is a microgrid controller, which takes the place of the grid operator on the grid in your system by orchestrating which sources turn on and off if required, and which loads need to shed if it needs. And load shed means just disconnect them to turn off if required to maintain stability. So the next slide here is microgrid connected. So this slide shows how, in a simple microgrid system, all of these devices link together. So you can see in the red, those are your line voltage hardwire connections that are all connecting back onto your main switchboard. And a microgrid controller exists controlling that switchboard, and those blue lines are all your communication conduits that the microgrid controller uses to monitor the system and control it. The cool aspect of this slide is it also shows the EV vehicle to grid charging, which is a real exciting technology that's just kind of hitting the market. We have plenty of vehicle to grid charging systems now, but it's mainly limited for vehicles that can export power. But the exciting part of this is they act like a battery energy storage system, and you can plug your car in and actually get paid to inject power back onto the grid when needed, instead of just paying money to draw power from the grid. So this is kind of a cool new approach the vehicle to grid is. So the key aspect of the microgrid is balance. We got to balance the supply and demand, just like on the actual grid. Generation supply has to always match electrical demand. So the microgrid controller takes on this role of grid operator, turns on sources, decides when to discharge and charge the batteries to maintain stability in real time on the system. Load prioritization and shedding sequences are key for this microgrid operation, and we'll include a slide later that kind of discusses what this load prioritization looks like. But in case of grid instability, you need to have some loads on your system that you're willing to shed so that you can maintain stability of the system even when you all of a sudden lose power, so lose any of your sources. Okay, so this is the implementation strategy. How can we practically implement a microgrid in the real world? So the cost of a fully built out microgrid is more often than not infeasible for most projects initially. This is true even for buildings that require emergency community services, such as utility or municipal operation centers, fire and police stations, and emergency shelters. With a microgrid ready design, the goal is to avoid large upfront capital investment and to plan for future flexible phased implementation of the microgrid. And we can do this by designing an adaptable electrical infrastructure and planning ahead for when you do have money, grant money, or if the market conditions change to make some of these systems more profitable so that they can pay for themselves. So for the microgrid ready design elements, for electrical distribution, you want to invest in mature electrical distribution technology. So that, like we talked about earlier, the microgrid ready or microgrid switchboard is mature technology that's been around for 30+ years. We want to provide those controllable breakers now and advanced metering early on the project so that you're basically ready to plug and play new sources and the microgrid controller without the total massive cost of upgrading your electrical distribution system later. The next element is control readiness. So providing communication conduits from your microgrid controller or the location that you plan on installing your microgrid controller is essential right away on your project. And these conduits need to go to all your power sources and your switchboards. The key thing, yeah, if the microgrid controller is not part of the initial build out, plan for it because it's probably coming in the future. So you want to make sure you have the pathways in place. Okay, then for future storage and generation. So we want to plan for space, at least on site, for future generation and battery energy storage system. When you do have money, you want to prioritize generators first. So generators being the backbone of the microgrid, you want to plan for that initially as much as you can so that you have the power that's required for the resilient operation of the building operationally. The next best thing to invest your money in is on the PV system. You get energy payback, sustainability benefits, and it can generate income for you on the system. And then the microgrid controller is there to kind of maximize the value of that PV system. And then finally is battery energy storage, kind of the last piece of the puzzle. And I recommend those to be the last thing to consider because we're expecting battery energy storage systems to advance greatly in the coming decades. So delaying the purchase of the BESS may be the best decision for your project after you prioritize generation capacity for reliability. Okay, so then the other aspect of designing for microgrid ready and to plan for the microgrid, even if it's not all coming right now, is to prioritize your loads within the building for selective operation. So if revising how all your loads are connected to your switchboard later is extremely expensive. So you want to plan for this, plan for load shedding now in your mind. Early on in the project. So the first branch is your emergency branch, which probably everyone has experience with. This is where you put all your life safety systems, and the emergency branch never turns off, so it's basically always on. The standby branch will have IT systems, access control, video surveillance, building automation, and then full systems for special areas in your building. So you might have a certain room or a certain portion of the building that you want that's critical for the operation of the facility. So then that would all go on the standby branch. The normal branch is the rest of your building, and discretionary loads are unique loads within the building that you may want to be able to turn off and not power without disrupting building operations. So a great example of this is EV charging, because we already talked about how huge of a load it is. For most buildings, those can go offline and barely impact the operation of the building. So that's maybe not true for all projects, but for many projects, that would be an example of a discretionary load you want to be able to turn off if required. Okay, so case studies. Kind of starting to run out of time, so I'll try to go through our examples here quickly. This is just an example of a project we're working on here in Oregon that's Microgrid Ready. So the electrical distribution in this case is designed and planned around a microgrid, and the microcontroller is planned to be in place because we do have a large PV system, but only one initial generator is being planned for, but we do have significant PV installed on day one. And this next slide kind of shows how it's organized. So we have, you'll notice the bottom is where your microgrid ready switchboard is. And instead of transfer switch schemes, it's all just done in the microgrid with the breakers switching, and you have a load priority applied to each of these. So in this case, we have emergency, standby, which is feeding freeze protection and IT systems, and then the pool, which is basically the first thing that will shed if required, and then normal is the rest of the building. So all of this comes directly into the main switchboard and gets managed by the microgrid. And then this next slide is just showing like what information needs to go along with a single line diagram to describe how the microgrid is going to operate. So we need an operating modes narrative that explains what is happening in blue sky mode and grid connected mode. Then what happens on loss of utility power or unacceptable power quality by the utility, which usually is like you're about to lose it, and how that transitions from blue sky to islanded mode. And then once you're in islanded mode, the load priority scheme basically activates. And then we have under that load priority scheme the shedding sequence. And in this case, we have EV charging gets shed, then site power, which is like sports fields lighting in this building specifically, which is a significant load, then the pool, then the normal power in the building, and then kind of finally optional standby. So it has this sequence in place so that it can manage the loads on the building's switchboard.
Okay, here's another example of a microgrid that we participated in Salisbury Square. It's in Randolph, Vermont. It is a community microgrid targeted towards an affordable housing development done by the Randolph Area Community Development Corporation. It features 9 single-family homes and 12 apartment units that are all tied together with a site-wide microgrid. Each of the buildings incorporates some type of rooftop solar, as well as battery energy storage systems. But rather than have all of these generation resources and storage resources tied independently to each of the buildings, they're tied together by a DC bus that is owned and operated by the utility provider, which is Green Mountain Power. They also own and operate the solar and battery, which allows them to assist in supporting standby loads during grid outages to this development, but also to participate in their overall management of electrical load and demand in this general area. So this is a pilot program that Green Mountain Power is supporting to trial how a small microgrid, community microgrid, might offer benefit to them as a grid operator in balancing supply and demand, as well as protecting some of these at-risk populations from what is generally seen as an unreliable utility grid in the Atlantic Northeast. So the microgrid features about 160 kilowatts of distributed solar. There's a megawatt hour of battery energy storage. As I suggested, is tied together with a site-wide DC direct current microgrid, which powers both AC and DC loads in each of the buildings. So it has some innovative features in that regard. Then dialing down one more layer to a single family home, which we had the pleasure of assisting with in Arlington, Virginia. This is a well-sized home, 4,000 square feet, Passive House certified, which really reduces the heating and cooling demands of the property. So we designed an electrical system that ties together 10 kilowatts of rooftop solar with 20 kilowatt hours of battery energy storage to allow the home during grid outages. So when the utility fails in Arlington, to allow the home and the owner to maintain key electrical loads in the property, including fridges and freezers, their heat pump, lighting, and minimum low voltage, as well as a warming or small oven, and support that operation during that grid outage. So we did some analysis on daily electricity consumption anticipated from that smaller standby panel, as well as what we would be generating from the rooftop solar and what we could store on site. And this is sort of an all renewable microgrid at a very small scale, which maximizes really the benefit of the owner's investment in solar and battery. And that is the end of our presentation. Thank you everyone for attending. I'm going to go to the questions here to see if we can respond to any questions. So the first one is, are any of these design components different in electrical utility deregulated areas such as Texas?
I can answer this. I'm not so sure there's any deregulated electrical utilities areas. In Texas, they still have, the utilities all still have their requirements. So the design components stay the same in all of the utility districts, but the specific implementation is going to vary. So if you're in California and you have to put in a battery energy storage system by code, according to Title 24, then your system's going to have a battery energy storage system. And then the particular utility requirements, like I was mentioning with the islanding, the grid connected and islanding mode, how that transfers, and the protection and coordination devices required to safely manage that are going to change from utility district to utility district. Those specific transfer requirements and protection and coordination requirements. And then other utilities are going to have different incentives. Like, for example, in Oregon here, there's a dispatchable generation program where you can get paid incentives from the utility to put your generators online and let them start them up. So if they need that on the grid. So in the grid connected mode, there's going to be quite a bit of differences in what the utilities offer as incentives and what they'll allow. But once you switch to islanding mode, it's pretty much the same thing everywhere, because you're disconnected from the utility at that point, and you're basically building under the electrical code.
Okay, any other questions from any of the other attendees? Okay, Alex, it looks like that's it from audience. Do you want
Yep.
to closing remarks?
Sure, yeah. So thank you guys so much for presenting. That was great. And thank you everyone for participating. We hope it was informative. I thought it was. And if you have any suggestions for improvements or suggestions for future topics, please send us a note. We love to hear that. Definitely getting some plans underway already for the next year. And even before the next year, keep a lookout for our next one, which is going to be in November. And if you have registered for this one, then you are already on the list, so you will get a notification. Thank you, everybody. Enjoy the rest of your day.
Thank you.